We're going to talk now about modeling mechanical vibrations with differential equations. We're talking about a system like a mass spring system where you have an object that vibrates back and forth. Hooke's law governs the motion. So let me draw you a picture here of your typical mass spring system. I like to put it on the side here. Imagine a spring like this, and there's a mass M attached to the spring. If we call this our x-axis, you can imagine here at position 0 is what we call the equilibrium position. This is where the mass will sit if it's just at rest. The spring isn't pulling it or pushing it. Now, if you stretch that to some position away from 0, say way out to here, then the spring will want to pull it back in the leftward direction. If you compress the spring so the mass is way over here, then the spring will want to push it back again towards the equilibrium. That's why we talk about the force acting on this mass as being some negative constant minus k. K will then be k is called the spring constant and will be by convention positive. So minus k will be negative times the position x. It's a negative constant because when x is positive, the force is in the leftward direction, the negative direction. When x is negative, the force is in the rightward direction. What does the motion of an object look like if the only force acting on it comes from Hooke's law, from the force applied by the spring? Well, let's just call the position now u. Change it from x to u. The book tends to use u in this situation. And we'll use Hooke's law that says the force is minus k times the position, in this case minus k times u. But also Newton's law, which says the force is the mass times the acceleration. Well, the acceleration is just u double prime. And so that force, which is m times u double prime, is the same, equal to ku. You put everything on one side, and you get this simple, beautiful second-order linear constant coefficient homogeneous differential equation, mu double prime plus ku equals 0. And that means that if you start the object, let's say position 0 here, you start with initial conditions u of 0 equals some position u naught, and u prime of 0 equals some other value u naught prime. You tell what it's doing at time 0. Maybe it's located here and moving in the leftward direction at the initial position. You find the unique solution to this second-order linear homogeneous constant coefficient differential equation that satisfies your initial condition, and you can tell what the motion will look like at all times in the future. That's easy. This is an easy one to solve, of course. The characteristic equation is just mr squared plus k equals 0. The solutions are clearly r equals plus or minus the square root of plus or minus, I should say, I times the square root of k over m. Remember, k and m here are positive, so it's easy to verify that these are the solutions. And that means that you have a fundamental set of solutions y1 equals cosine of square root of k over m t, and y2 equals sine of square root of k over m t. By convention, we're going to let omega naught, this is the angular frequency, be the square root of k over m. So this is just going to be cosine omega naught t and sine omega naught t. And so the general solution is going to be y equals some constant c1 cosine omega naught t plus a constant c2 sine of omega naught t. Let's talk about those solutions. We've talked about this in previous lectures, that when you have here a linear combination of sine and cosine with the same argument there, we can write this as some amplitude r times just a single cosine function. It'll be cosine of omega naught t minus delta, where here r squared will just be c1 squared plus c2 squared, and tangent of delta will be, this is c2 over c1. And when we write it like that, we can understand the motion really well. I'm sorry, that should, instead of y, I've been using the wrong variable, that should be u as a function of t. We're using u for our position function. So now if I plot u here on the vertical axis and here t on the horizontal axis, what will happen is you'll have just the behavior of the position of your mass at any time t. It will behave like a sine wave or cosine wave, phase shifted by some amount and with some amplitude. And it will just keep going on and on like that. The period, that's the time to get from one position back to the same position from here to here, will just be 2 pi over omega naught. You can see that's the time for this to repeat. Cosine has period of 2 pi, so in a time capital T is 2 pi over omega naught. All of this will just repeat.